Welcome back to the deep dive. We're here to, cut through the noise and get straight to what really matters in tech.
Glad to be here.
So today we're tackling something that's been buzzing around quite a bit, these large language models, LLMs, and their seemingly amazing reasoning skills.
Yeah, it's pretty impressive stuff. We're seeing models like OpenAI's O1, DeepSeek R1, Qwen, hitting or even beating human scores on tough benchmarks, especially in math.
Right, math is a big one, but here's where it gets, weird. Some recent research is hinting that these LLMs can get better at reasoning with hardly any supervision.
Or, even more strangely, with reward signals that are just random or plain wrong.
Exactly. It just doesn't sound right, does it?
Not intuitively, no.
And what's really interesting is this effect, these gains, seem mostly tied to certain models like the Qwen 2.5 family. You don't see it so much with others, say, Llama.
Which deepens the mystery.
So that's our mission for this deep dive. We're looking at a new paper, Reasoning or Memorization, Unreliable Results of Reinforcement Learning Due to Data Contamination. It's by Minky Wu and colleagues.
A really timely piece.
We want to figure out why this happens, what's behind these performance jumps, and ultimately, what does it tell us about how we should be evaluating these models? How much can we trust them?
Okay, so first off, let's establish why math is such a good test bed here.
Good point.
It's not just about knowing facts. It demands, precise symbolic stuff, step-by-step logic. That's why benchmarks like Math 500, AMC, Amy, they're tough. They really push the models.
Right, they're discriminative. And one way researchers try to boost these math skills is with something called reinforcement learning with verifiable rewards, RLVR.
RLVR, yeah. It's pretty straightforward in concept. The model tries a problem, gets the answer right, it gets a reward like a 1, gets it wrong, gets an yada.
Simple binary feedback.
Exactly. It's efficient, computationally speaking, and for math, where an answer is clearly right or wrong, it's a nice precise signal for training.
Okay, so that brings us back to the puzzle. Why would giving random rewards, or even wrong rewards, make Qwen better on these math tests, but not Llama?
Well, the researchers basically zeroed in on two main possibilities, two hypotheses.
Okay, what's the first one?
Hypothesis 1, data contamination. The thinking here is, look, Qwen 2.5 was trained on absolutely massive amounts of web data.
Billions, trillions of tokens.
Huge scale. And that data likely includes stuff like GitHub repositories, maybe online math forums, places where benchmark problems and their solutions might just be sitting out there.
So the evaluation questions might have accidentally ended up in the training data.
Of course. If that happened, then maybe these weird rewards aren't teaching reasoning at all. They might just be sort of nudging the model to spit out answers it already memorized.
Like a cue to recall, not to reason. Okay, that makes a certain kind of sense. What was the alternative idea?
The second hypothesis was about strong baseline math skills. Maybe Qwen's pre-training just made it fundamentally better at math than Llama to begin with.
So it starts from a higher level.
Yeah, and if it's already pretty good, perhaps even noisy feedback, these random rewards, look like they're helping, just because the baseline is so strong.
Okay. But you mentioned if that were true, wouldn't random rewards still work, even on a totally new, clean test?
That's the key question, exactly.
Yeah.
So how did they test this? They came up with a clever method, the partial prompt test.
Partial prompt? What does that involve?
Instead of giving the model a full math problem, they'd feed it just a piece. Like, say, the first 40% of the text, or 60%, or 80%.
Okay.
And then they check two things. Can the model figure out what the rest of the question should be? And can it still get the right answer, even with the incomplete prompt?
Interesting approach. What did they find?
The results were, pretty eye-opening. Take Qwen 2.5 Math 7b, give it just the first 60% of questions from the Math 500 benchmark.
Right.
It managed to regenerate the missing 40% of the problem text with a 54.6% exact match rate. That's pretty high.
Over half the time, it knew the exact wording of the rest of the question from just part of it.
Yeah. And even more telling, it answered 53.6% of these incomplete problems correctly.
Wow. So it wasn't just completing the text, it was solving the problem it completed.
Yeah, exactly. They even gave an example, a problem about 224 being a perfect nth power from Math 500. Qwen apparently just reproduced the original question text and the whole reasoning chain, word for word.
That sounds a lot like memorization. How did Llama do on this same test?
Oh, a completely different story. Llama 3.18b on the same 60% partial prompts from Math 500.
Yeah.
Its completion rate was only 3.8%, and its accuracy on those partial problems, just 2.4%.
Okay, that's a massive difference. 50-odd% for Qwen versus low single digits for llama.
Huge difference.
Yeah.
And they saw similar things with Quen on other benchmarks too, like AMC and AIM. It could generate whole reasoning chains, sometimes even with working Python code snippets.
Which again hints that it might have seen solved examples during training.
Strongly suggests it, yes.
Yeah.
But the researchers needed a control, right?
To be really sure it wasn't just superior skill somehow?
Exactly. So they brought in Live Math Bench, specifically version 2025-05. The crucial thing here is the timing. This benchmark was put together after the Quen 2.5 models were released.
So Quen couldn't possibly have seen this data during its pre-training.
Zero chance. And what happened? On this clean benchmark,
Yeah.
Quen's partial prompt completion rate
Let me guess. Much lower.
dropped like a stone, down to 0.0%, same as Llama, which was also 0.0%.
Okay. And the accuracy on these partial clean prompts.
Also plummeted. Quen got only 2.0% correct, which is right around Llama's 1.0%.
Wow. So on genuinely new data, that amazing completion and solving ability just vanished.
Completely vanished, which really drives the point home.
So what's the main takeaway from this part of the study then?
It points very strongly towards data contamination being the reason for those initial strange results on those standard benchmarks. Those gains Quen showed, especially with weird rewards, were likely echoes of memorized answers, not signs of real reasoning being learned.
Okay, so the contamination hypothesis looks much more likely than the strong baseline skills one at this point.
Much more likely based on this evidence, yeah.
But to really nail it down, they needed an even more definitive test, right? Something completely free of potential leakage.
Precisely. And that led them to create the random calculation dataset.
Random calculation sounds synthetic.
Totally synthetic. It's generated automatically using random numbers and math operators. Think complex numerical expressions written out in LaTeX.
Okay.
The key thing is, because it was generated after Quen 2.5 came out, and it's purely synthetic, there's absolutely zero chance the model could have encountered these specific problems during its training. It's a truly clean slate.
A guaranteed leakage-free zone. And did they use the same simple ERO1 reward system here?
Good question. No, for this data set, they actually designed a more nuanced continuous reward function.
Continuous. How does that work?
Instead of this pass-fail, it gives partial credit based on how close the model's answer is to the correct numerical result. It uses a formula like R1 0.5 minus BOB1, 0.5 minus BE5, places 0, B plus 1. Basically, the closer you are, the higher the reward between 0 and 1.
Okay, so it's not just right or wrong, but how wrong? Why the change?
They found this denser signal was really helpful for stabilizing the training process, especially for these potentially complex multi-step calculations. Binary rewards can sometimes be too sparse,
Right. You might be getting closer, but still get a 0 reward, which isn't very informative.
Exactly. So first, they checked Quen's performance on random calculation before any RLVR training its zero-shot ability.
Yeah.
It showed a clear pattern. The more computation steps needed for a problem, the lower Quen's accuracy, which is what you'd expect, really. It showed there was plenty of room for actual learning and improvement. It wasn't already acing these.
Okay, so it established a baseline and confirmed it was a real challenge for the model. Then came the RLVR training on this clean data. What happened?
This is where it gets really decisive. They trained Quen 2.5 Math 7b using different reward types on random calculation.
Let's start with a logical one. Correct rewards.
With proper, accurate rewards based on their continuous function, Quen's performance steadily improved. It got consistently better throughout training.
So it learned.
It genuinely learned. It even surpassed a tough threshold they called max at 16, showing it could handle more complex problems over time. Real skill transfer was happening.
Okay, that's a positive case. Now, what about the weird rewards? Random or incorrect?
When they used random rewards, the training just didn't work reliably. It became unstable, performance fluctuated, no consistent improvement. Basically, noise in, noise out.
No magical gains this time.
None whatsoever. And when they used incorrect rewards, essentially, rewarding wrong answers and penalizing right ones,
That must have been bad.
performance completely collapsed very quickly. The model basically unlearned any ability it had.
So on clean, uncontaminated data, the whole premise of random or incorrect rewards helping just falls apart.
Completely. It shows that reward fidelity is absolutely critical once you remove the confounding factor of data contamination.
And did they check llama on this random calculation dataset too?
They did. Llama 3.18b instruct showed the same pattern. Only accurate rewards led to improvement. When they fed it spurious signals, random or incorrect rewards, its accuracy actually dropped below its initial baseline.
Okay, so both models behaved logically on the clean data. Only correct feedback helped.
Correct. This pretty much seals the deal. It rules out that second hypothesis, that Quinn's baseline math skills were somehow so strong that even random noise helped on the contaminated benchmarks. That effect disappears on clean data.
It was the contamination all along.
It really seems like it was primarily the contamination queuing memorized answers.
So let's pull this together. What's the big picture here for us, for you listening? What does this research really tell us about LLM capabilities?
Well, first, it clarifies things about Qwen versus Llama. The study does show that Qwen 2.5 seems to have stronger inherent math abilities than Llama 3.1, at least on this kind of calculation task, when trained properly with correct rewards on clean data.
Okay, so Qwen is good at math.
It seems to have a stronger baseline, yes. But, and this is the crucial but, that underlying strength was not why it showed those weird performance boosts with random rewards on benchmarks like Meth 500.
Right.
That effect was an artifact of data leakage.
Right, the two things are separate. It's actual skill versus the illusion created by contamination.
Precisely. And that leads to the broader implication. We desperately need trustworthy evaluation methods.
Meaning clean benchmarks.
Clean benchmarks are essential, yes, like live math bench or synthetic ones like RandomCalculation. And also, we need to test methods across different models, different architectures. We can't just draw conclusions from one model family that might have unique issues, like Qwen apparently did with contamination on certain tests.
So if someone is developing a new training technique, say a new RL approach, they need to show it works on clean data and preferably across different base models.
That would be the gold standard for making reliable claims, yes. Otherwise, you risk fooling yourself, thinking you've made a breakthrough and maybe you've just found a clever way to exploit test set leakage.
Okay, so practically, how does the AI research community ensure this happens more often? What needs to change?
It's probably a few things. Better practices around documenting and cleaning pre-training data, maybe, though that's incredibly hard at web scale.
Yeah, finding every possible test question in petabytes of data sounds impossible.
It's super challenging. So perhaps more emphasis on creating and using new, verifiably clean benchmarks is key. And maybe a cultural thing, too. A bit more skepticism, more replication studies before we accept really surprising results at face value.
So for you listening, why should you care about all this? How does it help you?
I think it makes you a smarter consumer of AI news and claims. You see a headline, AI achieves amazing reasoning. This helps you pause and ask, okay, but how?
Right. Was it tested on data it might have already seen? Were the conditions clean?
Exactly. Is it showing genuine generalization, real understanding, or is it more like a superpowered parrot recalling things it was trained on? This research shows that distinction is absolutely vital, especially when we talk about reasoning.
It encourages that critical thinking layer. Don't just take the performance number. Ask about the process, the evaluation's integrity.
Definitely. It's about understanding the difference between performance on a specific test, which might be flawed, and the model's actual underlying capabilities.
So the key insight here really is that sometimes what looks like AI magic, like learning from random noise, might just be a data trick.
A trick of the data, yeah. It highlights that for genuine progress, especially with techniques like reinforcement learning, getting the reward signal right and using clean data are just fundamental, non-negotiable, really.
Okay, let's leave our listeners with a final thought then. As you go about your day, interacting with AI, reading about the next big breakthrough, maybe keep this in mind.
Yeah, think about how this whole issue of contamination versus real skill might apply elsewhere.
How might it change the way you look at information, maybe not just from LLMs, but from any complex system or even human experts that need to dig into the why behind a surprising result?
And are there other areas, maybe beyond math or even beyond LLMs, where we might be mistaking impressive recall or pattern matching for deeper understanding? It's a really interesting question to ponder.
Definitely something to think about. Thanks for breaking that down.
My pleasure. Fascinating study.